Let's move on to some more neuroanatomy. This video is going to be on other structures in your brain that help you control your movement. These are going to be your cerebellum and your basal ganglia. We'll start with the cerebellum first. Let's just go over some anatomy you've learned thus far. So we'll draw our brain out. You had your frontal lobe, your parietal, or frontal, parietal, occipital, and your temporal. And because we're talking about movement, we're going to be talking about the motor cortex here. That's what we said helps control movements. Now we're going to talk about other structures that help control your movement. So let's take this anatomy one step further. If we're talking about the entire CNS, that's your brain and your spinal cord. So you have your spinal cord. There's a part of your brain that connects the two. We call that your brain stem. And we'll go over the anatomy of your brain stem in later videos, but just know there's a brain stem. All right, brain stem. And then the cerebellum, which is the topic of this video, is going to be this giant goober on the back of your occipital lobe, on the back of your brain stem. This is your cerebellum. And this is what helps control your movements. So let's look at your cerebellum in a little bit more detail. Recall your brain is split up into two hemispheres. So if we turn this way, and we look at the two hemispheres, it would make sense that your cerebellum also has two hemispheres. And it does. And it's joined, and the hemispheres are joined by something called the vermis. So this is like your lateral hemisphere. The confusing thing, however, is that we don't break the cerebellum up to the left and right hemispheres. Instead, we break it up to anterior and posterior lobes. So the anterior portion would be your anterior lobe. Posterior portion would be your posterior lobe. And then you have this small flat lobe on the bottom called your flocculonodular node. So it's confusing, they break it up in the anterior and posterior, but just know for the functional purposes, the fact that you have two lateral hemispheres is kind of more important. If you have damage on the lateral side, you'll have dysfunction of your lateral extremities, or just right extremities. And that's easy to remember. If you just kind of stick your arms out and your legs out, that's what's affected, so your extremities. So it's easy to remember your lateral sides of your cerebral hemisphere is going to affect your lateral extremities. And if you affect the central area, then you'll affect kind of the central region of your body. And this really helps with things like keeping your balance, keeping your gait. Okay? So I'll write midline gait. And that'll be like your vermis. Now if you dissect the cerebellum, you'll notice that inside it's very, very complicated. And you don't need to know all the complications, you just need to know there are numerous nuclei that just helps it process information. So if we work from lateral to medial, you have your dentate nuclei, your emboliform nuclei, your globus nuclei, and your fastigial nuclei. The common mnemonic is don't eat greasy foods. You can use anything, but you should just know what they are lateral to medial. All right? So, all right, dentate, emboliform, globus, and lastly, fastigial. And these nuclei just help you process your information. So we're talking about all this information. How does it process it, and how does it send it to the motor cortex? I mean, it's all the way down here, right? How does it do that? Well, it'll go through your brainstem to get there. And the reason it can go through your brainstem is because it has these stalks that connect it to your brainstem. And these stalks we call peduncles. Peduncle is like a botany term that means stalk. So you have 3 stalks that connect it to your brainstem, and because it can connect, it can send information back and forth. I mean, it's sitting all the way back here, but it needs to get to where it needs to go. So it has these peduncles and allows it to send and receive information. So you have 3 peduncles. I just love that word, peduncle. You have one that's I drew way too many peduncles. You have one that's on the inferior end, one in the middle, one superior. So you have an inferior peduncle, a medial one, and then a superior one. So the big picture is your cerebellum receives motor information and then kind of processes it. We call that input. And then after it processes it, it'll send information out. We call that output. So the inferior and the medial is going to be where you get your input. The inferior, being closest to your body, is going to get input from your limbs and your body. So I just write input from the limbs, and it's going to be ipsilateral input. Easy to remember, I and ipsilateral, I and inferior, and then easy to know is input from your limbs because it's the lowest peduncle, it's the closest to your limbs. Medial will get input from your brain. Our brain and our body is going to have to work together, so you're going to need input from both. So once from your limbs, once from your brain. So this is going to be from your brain, or your cortex, or your cerebrum. And this is going to be contralateral. So it takes all that input, all the information, processes it, and then we'll send info out. Out from the top peduncle, because that's the one closest to your brain. So the top one is the output. And that just gives output. That just gives output information. And that goes contralaterally. That's a lot of contralateral, that's a lot of ipsilateral. How do you keep it all in order? You know, what's the most important thing you gotta take away from this? The most important thing you gotta take away from this is that cerebellar lesions affect your ipsilateral side. So you have a right cerebellar lesion, it will affect your right side. Why is it ipsilateral? Well, we said it'll take all this input and then it'll shoot that output contralaterally to your motor cortex, and your motor cortex also works contralaterally. So you send it contralaterally and it'll send it back contralaterally, so it kind of cancels itself out. And so it becomes ipsilateral. That is your cerebellum. Now let's see what can go wrong. One of the big ones is Chiari 2. We have our brain over here, and your brain sits in your skull. So you have your skull that kind of surrounds and protects it, and it comes all the way around. Well, your skull will need a hole in the bottom, otherwise your spinal cord won't be able to go through, and it's going to need a pretty big hole because your spinal cord is pretty big. We call this hole the foramen magnum. Magnum being big, foramen being hole, so big hole. And so you have that foramen magnum to let your spinal cord sit through. All right, and your cerebellum just kind of lays against that. In Chiari 2, for some reason, your cerebellum herniates through that hole, especially the midline structures, because it can go right through the middle of the hole. And that'd be your vermis, right? If it herniates through that hole, then it'll compress things in that foramen. Some things that could compress is going to be your ventricular system. Recall your ventricular system is just this like water balloon system that kind of keeps your brain buoyant. Then you had your lateral ventricles that drained into your third ventricle. And that third ventricle will go down near the cerebellum through something called the aqueduct. And right by your cerebellum, you'll have your fourth ventricle. And so when it herniates through that foramen magnum, it'll compress the living crap of that fourth ventricle. So I'll write compress, fourth, and also the aqueduct. Why does that matter? Well, when you compress the aqueduct, it won't be able to drain what's in it, CSF. So that CSF will build and build and you'll get hydrocephalus. Hydrocephalus. From all that aqueduct stenosis. Patients that have Chiari 2 malformation often have increased risk of other malformations. The main one being meningeal myocele. What is meningeal myocele? We talked about that a few videos ago, so hopefully you remember. That's when your meninges and your spine, that's the myelin part, herniate out through your back. Yeah, that's the most severe form. You'll have neurodeficits in that area. That is a neurotube defect, so increased alpha-fetoprotein, increased acetylcholine esterase, all that good stuff. So just keep that locked in the back of your mind. Why do they call it Chiari 2? Why does it just jump automatically to 2? Is there a Chiari 1? There is a Chiari 1. Chiari 1 is just a milder form. So you might have slight herniation. Usually it's asymptomatic. So right, Chiari 1, asymptomatic. Next is Dandy Walker. Dandy Walker is when your vermis, here's that vermis again, that stinking vermis, doesn't develop, so agenesis. And if it doesn't develop, then other things just kind of take its place. So that fourth ventricle that's near it already will kind of blow up and take its place. So I'll say fourth ventricle enlargement. And so you'll also see signs of raised ICP from that increased fourth ventricle. Movement disorder, you're also going to see movement disorders because you don't have a cerebellum. And like Chiari 2, people that have this have an increased risk of other malformations. The main one being spina bifida. What's spina bifida? In the same category, same neural tube defect category as meningeal myocele, but this is the most mild one. This is just when you have a split in your spine. Yeah, not really a big deal. You might see a tuft of hair, dimple, recall all those physical findings. So raised ICP, movement disorders, I mean, these two are very, very similar. How can you tell them apart? Well, you do an imaging, and then if you don't see a cerebellum, then you know it's Dandy Walker. See this really, really black mass, aka this cystic enlargement of your fourth ventricle, then it's Dandy Walker. If you do see the cerebellum, it's just going, herniating through towards your spine, then it's Chiari 2. That is your cerebellum. Let's talk about your basal ganglia. So your basal ganglia is a group of structures in your brain. And so I'm going to try and draw it. So if we look at the brain like this again, you have your two hemispheres. And if we blow this hemisphere up, then you'll have these internal structures. They kind of look like this. All right, there's a better picture in my notes, but you get the gist. And all these structures come together and help us control movement. And all these structures are called the basal ganglion. Now this first structure right here is called the caudate. This deals with the brain, the cognitive portion of movement. So just write cognitive. This structure here is called the putamen, which helps control the motor aspect of it. So you have the brain, now you have the motor. And because these two go so well together, we sometimes group them together and call it the striatum. So if you see the word striatum, don't get confused, it's just grouping these two together. Down here, it's going to be your globus pallidus. Sometimes broken up into external, internal. So I just write GPE, globus pallidus external, GPI, globus pallidus internal. And the function of this is that it constantly makes GABA to inhibit movement. And that's good. At our resting basal level, we don't want to be moving. This is our resting basal level, we don't move. We don't want to be like moving constantly, that'd be terrible. So at our resting level, we just have this constant GABA inhibition to stop us from moving. But what if we do want to move? Well, if we do want to move, then your striatum, striatum will tell your globus pallidus to stop. Stop producing this GABA, stop inhibiting us, let us move. So it tells us to stop and then you can move. How does it tell us to stop? Well, how does your brain inhibit anything? It'll release GABA. So it'll release GABA to stop the release of GABA. So they sometimes call it, sometimes they call it inhibiting the inhibitor. Again, another double negative, they cancel each other out. And that way you get to move. Next up is your subthalamic nucleus, or STN. This is a main excitatory one. So it releases glutamate, works on NMDA. And last but not least, your substantia nigra. Which contains dopamine. And dopamine might be the most important neurotransmitter in the whole basal ganglia. Why? Because dopamine is what tells your basal ganglia to either move or not move. And it does this by binding to dopamine receptors. So D1 receptors or D2. And if it wants it to move, then it'll bind your D1 receptor. So move. And it's very direct. It'll basically tell your striatum, hey, tell the globus pallidus to knock it off. Stop it from producing GABA, stop it from inhibiting. So it's very direct. It just says, do this right away. So we call this the direct pathway. That's easy enough. Sometimes you write it as D1 rect. That way you always know it's D1 is the direct pathway. If you don't want it to move, then you hit your D2 pathway. So I'll say, don't move. Now this one is very, very, very complicated. Okay, it's not as easy as just saying, globus pallidus, make more GABA, stop us from moving. No, it's way more complicated. So we call it indirect because it basically works through your entire basal ganglia. Indirect. I won't get way too into it, but if you want to know how it works, just know that it will talk to your striatum again. And again, it will inhibit your globus pallidus. Your globus pallidus will stop producing GABA. And there's an extra step. It will work on your subthalamic nucleus. So it'll stop producing GABA, stop producing that inhibition, especially on your subthalamic nucleus. And we say your subthalamic nucleus makes all this excitatory hormone. So you have a lot of excitement. All that excitement will go back into your globus pallidus, which is your inhibitory. So it just kind of loops itself back around and then increases more inhibition. That way you stop movement. That's how it inhibits itself. So it kind of does a whole loop and basically increases GABA and inhibition. And that is how your basal ganglia works. Hope you enjoyed the video. Thanks.